Hello, my name is Hannah Chu, and I am a comprehensive ophthalmologist. Today, I will be taking you through the dissection of the human eye. The human eye is a very intricate and complex structure. There are many specialized cells and tissues that make up the different structures of the eye that produce vision and allow one to see. The anatomy of the human eye is best understood and shown through the process of dissection. Here we have a human eye for training purposes, but other times we can also use other mammalian eyes, including those of sheep and cows. Although there may be some differences, the foundational structures are very similar. Now, begin by examining the front of the eye. How about the sclera, the white part over here? The sclera is the tough, dense, irregular connective tissue to which the extrinsic eye muscles attach to move the eye. Look at the back of the eye and you will see the optic nerve, the cable that connects the eye to the brain. Pay attention closely and you will see the separate fibers of the nerve and the myelin surrounding them as they transmit visual information from the eye to the brain. At the front of the eye is the cornea, the clear window that allows light to enter the eye and focus it on the retina. Take note that here the cornea is not transparent as seen in the living state. Although corneal opacities can occur in several eye problems, with death, the cornea becomes opaque due to loss of the ATPase pump within the endothelial cells. Recall that the cornea is bathed between the precorneal tear film outside the eye and the aqueous humor within the eye. The ATPase pump is what is responsible for maintaining detergescence or a state of dehydration of the cornea. The pump actively uses energy to drive fluid out of the cornea, and without viable endothelial cells and an ATPase pump, the cornea stroma will become opaque. In cataract surgery, we create a main wound in the cornea using a keratome, and a paracentesis wound with a 15-degree blade. In corneal procedures, we use a trephine to make a perfectly round excision of the cornea. In this case, we will first use a pair of microforceps, or .12s, to provide countertraction and a 15-degree blade to create the first opening. Then we will use scissors to remove the rest of the cornea, carefully following the curve. As you do this, you will notice the aqueous humor flows out from the anterior chamber of the eye. The aqueous humor not only provides nutrients for the eye, but it also maintains the pressure in the eye, giving it its shape. The eye now appears deflated because the aqueous humor has been drained. Take a close look at the cornea and recall its 5 layers. The layers of the cornea includes the epithelium, Bowman's layer, the stroma, which makes up 90% of its thickness, Descemet's layer, and the endothelium. Here is a tip for remembering the layers. Descemet's is deep and Bowman's is above. Using the same blade, make a small cut through the sclera. Cut 4 to 5 millimeters posterior to the limbus in the anterior-posterior orientation. You may see some fluid flowing out of the eyeball. This is the vitreous humor, which is the clear structure made up of 99% water and some collagen and hyaluronic acid to hold it together and give it its gel-like properties. You may also have noticed pigmented tissue coming from your incision. This is known as uveal tissue, which we will demonstrate later. Continue to cut the sclera all the way around the eyeball. Arrange the 2 hemispheres of the eye side by side and appreciate how the vitreous humor is a gel-like structure that sticks to the inner eye by turning it over. During the processing of these eyes, the vitreous may segregate to one part of the eye and the liquefied vitreous may be lost. Anything anterior to the lens of the eye is known as the anterior segment. Anything posterior to the lens is the posterior segment. The retina lines the posterior segment and extends forward to the ciliary body. Note that the edge of the ciliary body where it connects to the retina is serrated, giving this area its name, the ora serrata. I am now pointing to the lens of a phakic eye. The lens has an ellipsoid biconvex shape and works together with the cornea to refract or focus light on the retina at the back of the eye. The lens consists of the lens capsule, the lens epithelium, and the lens fibers. The lens epithelium lines the front of the lens under the capsule and divides over time into lens fibers. A cataract is an opacity in the lens and is very common in people over the age of 40. Here is a pseudophakic eye in comparison, which means this eye had previously undergone cataract surgery, where the lens was removed and replaced with a clear artificial implant called an IOL, or intraocular lens. This is the posterior chamber IOL. During cataract surgery, an eye surgeon creates an opening in the anterior capsule of the eye and places the IOL through this opening into the remaining capsule or bag that previously held the natural lens. A PC-IOL is the most common type of IOL placed in the eye. However, an anterior chamber intraocular lens, or ACIOL, may be inserted in front of the iris in the anterior chamber in certain circumstances. In a phakic patient, the lens is held in place by the zonules, which attach the lens to the ciliary body. The zonules in turn are controlled by muscles within the ciliary body that can contract and relax, which in turn changes the shape of the lens. This is what controls accommodation, the process of being able to focus at far or at near. The iris, located between the cornea and the lens, divides the anterior segment into the anterior chamber, the space in front of the iris, and posterior chamber, the space between the iris and lens. Note that the back of the iris is pigmented in all different eye colors, blue or brown, due to the iris pigment epithelium lining the posterior surface of the iris. Also note that the iris is continuous with the ciliary body and ultimately the choroid, the layer under the retina. These three tissues, the iris, ciliary body, and choroid, make up the structure called the uvea. Let's turn our attention to the retina. Axons of the retinal ganglion cell form the optic nerve, and therefore the retina is firmly attached around the optic nerve. Turn the eye over to confirm that this corresponds with the optic nerve at the back of the eye. Using forceps, peel the retina away from the choroid. First, notice how the retina easily peels off the choroid. In the living eye, when the retina separates from the choroid, it is called a retinal detachment and is due to a buildup of fluid in the potential space between the neurosensory retina and the underlying retinal pigment epithelium, or RPE, which lines the external surface of the retina. Note that the optic nerve is only about 1.5 millimeter in diameter within the eye. It is thicker outside the eye as the optic nerve is sheathed by myelin. Recall that the retina is transparent in a living eye as it must allow light to travel through it from the vitreous to the photoreceptors, which line the external surface of the neurosensory retina. Here you may notice that the retina is not transparent. This is because, much like in the cornea, it has become edematous in the non-living state. You will see the macula here, between the supratemporal and infratemporal retinal arcades, which enter the eye from the center of the optic nerve and divide into 4 quadrants of the eye. The retina contains photoreceptors that detect incoming light. After removing the retina, you can see the underlying choroid, which is a pigmented layer. Between the retina and the choroid is the RPE, which we mentioned. Aside from acting as a scaffold on which the photoreceptors sit, the RPE has many functions, including vitamin A metabolism for the photoreceptors and forming the outer blood-retina barrier. The choroid and RPE are pigmented to capture extraneous light that is not absorbed by the photoreceptors. This acts as a heat sink to reduce the temperature within the eye and reduces background noise to allow for more refined vision. The choroid is also a very vascular layer which nourishes the very metabolically active photoreceptors. Note the difference between the retina and the choroid. Where the retina is pale here, the choroid is quite pigmented. This concludes the dissection. This activity was supported by the Department of Ophthalmology and Vision Sciences at University of Toronto. We hope that you found this video to be interesting and useful for your own preparation for the dissection that is coming up. Thank you.